Hi there, welcome back. In this slice of physics, we're going to look at an example problem involving static and kinetic friction. We're going to see whether a forklift can push a pallet down the floor or not. Let's take a look at this question. It says that a 70 kilogram loaded wooden pallet is sitting on a wooden floor. A forklift pushes on it with a horizontal force of 350 Newton to the left. Show that this force is enough to move the pallet. That's our first task. And then it says if the forklift stops pushing the pallet after it reaches a speed of 6 meters per second, how far does the pallet slide before it stops? At this stage, what minimum mass needs to be added to the pallet to prevent the force of 350 Newton from being able to slide it again? And then it gives us the constants, the coefficients of static friction and kinetic friction for these wooden surfaces. Okay, there's a lot to do here, several parts. So let's get started with the first one and get started with our solution steps or recipe. Our first step is to draw a picture. So I'm going to show the floor over here. The pallet is sitting over here and it's loaded with stuff. And the whole thing has a mass of 70 kilograms. And then we got a forklift pushing on it to the left with a force of 350 Newton. And our first step is to show that this force is enough to start this pallet sliding down the floor. The condition we need to start the slide is that the pushing force must be greater than the maximum static friction. So let's see if we can figure out the maximum static frictional force in this case. So next step, as always, is a free body diagram. So I got the object over here represented by this dot. So as I go around it, I see that it's got a contact with the ground, which gives me normal force and frictional force. And it's got contact here with the forklift, which gives me the pushing force. Those are the only three contact forces I have. And then I have the usual weight as a long-range force. So here's my weight acting straight down. Here's my normal force. Here's the pushing force to the left. And here's the frictional force to the right. We kind of know that it's a kinetic friction because the question tells us that it's moving, but let's first confirm that and then we'll put the subscript over here. Then we got our axes, X horizontal and Y vertical. This pallet may be moving horizontally, but it's certainly not moving vertically. So that gives me a condition that sum of Fy has to be 0 because this object is in equilibrium along the y-axis, and that gives me n minus w equals 0 or n equals w, and w is nothing but mass times the acceleration due to gravity, which in this case is 70 times 9.8, and that gives me a normal force of 690 Newton. It's always good to find normal force in problems involving friction because we know that it figures in both the maximum static friction as well as in the kinetic frictional force. Next, since our first objective is to show that this force is enough to move the pallet, we need to show that the pushing force is greater than Fs max. That's when we can start moving anything. So let's figure out Fs max. We know the equation for Fs max is mu s times n. I know both of these things. Mu s is given to me as 0.50 times the normal force is 690 Newton. So this gives me a maximum static frictional force of 345 Newton. And since our Fp is 350 Newton, we have shown that that's greater than the 345 Newton maximum frictional force. So we have shown that the object will slide. So we're done with that first part. And now that we've shown that it's actually moving, we can go back to this free body diagram and show that we're dealing with a kinetic frictional force. We know that kinetic frictional force Fk is nothing but mu k times n, and so that's 0.20 times 690 Newton, and that gives us a value of 138 Newton. So you can see that the frictional force grows from 0 all the way to 345 Newton, but once it gives up and the object starts moving, the frictional force immediately drops to kinetic friction of only 138 Newton, which is what we meant by saying it's harder to start things to move than it is to keep them moving. So in this situation, not only is the pallet going to be moving to the left, it's actually going to be accelerating to the left because the applied force is a lot bigger than the frictional force. I showed this arrow as too large in hindsight because I didn't know what its value was to begin with. So for the next step, the forklift has stopped pushing. So if I draw the free body diagram now, I still have the same weight, I still have the same normal force, and I have the static frictional force that acts to the right, and that's it. I don't have a pushing force anymore. That's gone. Move this over here to make some room. And now the y-axis doesn't give me anything new. It's the same as before. But on the x-axis, I only have one force. So my sum of forces along the x-axis is just plus Fk. That's the only force. And that gives me plus 138 Newton. And if I know the force and the mass, I can get the acceleration. So going back to this second law, sum of forces in the x direction equals m times ax. And when I put the values in now, I get 138 Newton equals 70 kilograms times ax, which when I solve for ax, it is 1.97, or down to two significant digits, 2.0 meters per second squared. So I got the acceleration. I also have the initial velocity. It tells me that the forklift stops pushing once the pallet reaches a speed of 6.0 meters per second. But that 6.0 is a negative because it's moving towards the left. The pallet was being pushed to the left, so when the forklift lets go, it's sliding to the left. Do I know VF? The question tells us that the pallet comes to a stop, so VF is simply 0 meters per second. We do know that as well. And what it's asking for is delta x. That's what it wants us to find out. And we know the equation that ties VF, VI, A, and delta x. If you remember, that is VF squared equals VI squared plus 2 times AX times delta x. So now I can put these values in. VF squared is simply 0 squared. VI squared is minus 6. The whole thing gets squared, the negative and the 6. 2, AX is a plus 2.0, delta x. And when you solve that, you will get delta x equals minus 9.0 meters. So it tells us that the pallet will continue to slide for 9 meters to the left after the forklift stops pushing. Okay, now the last question. Once the forklift comes to a stop, it says how much minimum mass needs to be added to the pallet to prevent the force of 350 Newton from being able to slide it again. So it's asking for us to figure out the minimum mass, which means I barely need to get the static frictional force equal to 350 Newton force that's applied. As long as static frictional force equals that, or just barely over that, so it could be 350.0001 Newton, that's enough to prevent this from moving. I can certainly put more mass and prevent it from slipping, but since it's asking for minimum mass, I need to take that boundary condition where the static frictional force grows just above the applied force of 350 Newton. And since static frictional force can grow all the way to maximum static frictional force, in this case, we want the maximum static frictional force to just be over 350 Newton. So now we know from equation that Fs max is nothing but mu s times n. For maximum static frictional force to grow to 350 Newton, let's see what the normal force needs to be. We know that mu s is still 0.5, that was given to us, times n. So this gives me a normal force of 700 Newton. And finally, because along the y-axis normal force equals the weight, that tells me that the weight is 700 Newton for the pallet with the added weight, and that equals mass times acceleration due to gravity. And this gives me the mass of the pallet that can't be slid by a force of 350 Newton as 71.4 kilograms. I'm going to carry one extra significant digit since it's an intermediate step. And the final question we're being asked for is what is the minimum mass that needs to be added. So if this has to be the total mass and I started with 70 kilograms, the minimum mass I need to add would simply equal 71.4 minus 70.0. which will give me 1.4 kilograms. So if I simply add just 1.4 kilograms, static friction will grow to a value that's enough to prevent the 350 Newton force from moving the pallet. So this example gave you good practice on working with free body diagrams, both in an equilibrium situation and in a dynamics or accelerating situation, and it gave you practice on working with static and kinetic friction as well.